All right, there we go. Back to full screen. Well, thanks again for the invitation to speak here today. As you've heard, I've been doing the California wildfire circuit so far this year. Usually, this is the off season in the sense that it's not the time of year when we're talking about wildfire events that have recently unfolded. But of course, what everyone's talking about this year is what happened in January. And still the just sort of reeling from the effects of that. Uh, and coincidentally, well, I'll back up to that in a moment. But first, I just wanted to say that I am a climate scientist with the University of California Agriculture and Natural Resources, also known as UCANR, as well as with the National Science Foundation, National Center for Atmospheric Research. So I am a climate scientist, but I also study climate adjacent hazards, including various kinds of extreme weather, including extreme fire weather, and also increasingly the behavior of wildfires themselves, both in a warming climate and as it's changing for other reasons as well. And somewhat coincidentally, as you heard, I am indeed traveling, so this is not my usual setup. But that's actually because I'm in and around the Bay Area today. 2 days ago, as it turns out, somewhat coincidentally, I didn't realize this project was going on at the time. I was driving from Palo Alto to Santa Cruz, and I decided to go the long way since I hadn't been up on Skyline or down Highway 9 in some years, not since the 2020 CZU complex. And I actually ended up going up Page Mill on Thursday. And it turned out that there was the major Los Altos Hills, sort of the evacuation corridor fuels reduction project was actively ongoing. So I was stuck in the opposite direction of the one lane traffic control for a while, but I was happy to see it. Happy to be stuck and sort of watch that process unfold with vegetation clearing along, essentially along that road shoulder. And I think most folks in this audience have been on that road more than once, and so you know how narrow and windy it is. And so it really is one of those places where whenever I would go up years ago in the back of my head, it was always something that was lurking in the back of my head. So it was totally by coincidence. Didn't even realize that project was ongoing this week, but I can confirm that it was happening this week because I was there. And I also ended up coming down back up the Coast Highway up to the North Bay yesterday evening. And I hadn't actually seen the coast side of the CZU burn um, since it occurred. And so that was an interesting experience too. I took some photos. Didn't incorporate them into this presentation today, but I think there's some interesting lessons from sort of looking at the both the recovery in terms of people's homes and communities, and also the ecological recovery, in some cases quite robust, in other cases the lack thereof, depending sort of on where and the other details of those fires. But I just thought that was something that folks in the room might appreciate. That this is, I literally stumbled across just this week the Los Altos fuel reduction project along the major evacuation route. Um, so, I think that I probably don't need to motivate this talk too much in the sense of I think everybody who's present is aware of why this is all important, but I think some of the statistics still bear repeating, which is that although acreage is definitely not the most nuanced metric of wildfire, because of course you can have beneficial, large, but lower intensity natural fires. You can also have highly destructive, very small fires. Think about the Oakland Hills fire in the early 90s, for example. Not particularly large, but hugely destructive. That said, we have better records of the size of fires going back longer than we have records of the actual intensity of fires. And so it is still, though an imperfect metric, a useful one in comparing how things have changed over time. And to that end, we have seen just in the last decade in California now 13 of the 20 largest contemporary wildfires going back 100 years or more. And six of them occurred just in 2020. The CZU complex was one of the ones that occurred in that year. But probably more importantly, more concerningly, 15 of the 20 most destructive wildfires in California history have occurred in the past decade, including five in 2020, and then already this year, due to both of the fires in LA, two of the 20 most destructive again just in the last few months. Nine of the 20 deadliest fires, another really important metric because this is something that we didn't used to see at scale in any regularity in California, were direct deaths from wildfires in the double digits. Um, in this case, actually, two of them occurred both in 2020 and then again this year. Both the Palisades and the Eden fires made it, unfortunately, onto that top 20 deadliest list. And this is a statistic that shocked, I think, even me when I was looking at the numbers. But this is sort of the deadly disaster of contemporary California. More people have been killed directly by wildfires. This is not counting indirect deaths or illness or morbidity from smoke or evacuation stress or anything like that. But more people have been killed directly by California wildfires in the last decade than in all earthquakes in the entire state cumulatively since 1940, and in any earthquake since the Great Quake of 1906 in San Francisco. So this really has become the headline in terms of California disasters. It won't necessarily always be that way. It certainly won't be that way in every individual year. But, in the last decade, this is the headline story for a good reason. And the other thing I wanted to point out, if you look at the plot on the right showing the number of acres burned since the mid 80s in California, this is just as far back as this particular data set goes uh, which is that obviously the average has increased since that time. But the more interesting thing, I think, is that it actually isn't the ordinary years that have gotten much worse. It's the extraordinary years that are dramatically worse. But we still see a lot of relatively quiet years. Look at 2022 and 2023. Those would have been very much fitting in with the early 2000s, the 90s, or even the 80s in terms of the acreage burned. But most of the other years in the last decade certainly would not have. So what we actually see, more than an increase in the average acreage burned in California, is an enormous increase in the variability, in the wildfire whiplash from year to year, if you will, driven almost entirely not by decreasing minor years, but by large increases in the acreage burned and the structure losses and the lives lost in the very worst events and the very worst years. So, what's driving this? Well, I'm a climate scientist, so I will focus on that piece, but I always think it's important to just drive home the point that that is not the only reason why this is happening. In fact, part of the reason why things have gotten so bad so quickly is that it isn't just one thing, a single driver that's making things worse, but it's a confluence of multiple factors all pushing in the direction of increasing risk at the same time and either adding or multiplying each other. One is that more people than ever before live in high risk zones. Essentially, there's been population expansion into high risk fire corridors. So you can imagine how, even if there'd been no other changes at all and just the same historical repeating pattern of fires we saw before, that would probably result in more structure exposure and more structures burned. We also have the legacy of various types of suboptimal land management from over the past 1 to 2 centuries. And in forests, this often means essentially we excluded natural fires for so many years that there is now a buildup of forest fuels that wouldn't have occurred naturally. But this is also true for different reasons in other ecosystems. In grasslands, for example, we have huge numbers of invasive herbaceous plants now that are both more denser and more flammable than their native counterparts. And in the chaparral environment in Southern California, we actually have potentially too many fires relative to what would have occurred naturally. And so now what happens is we are exceeding the natural fire frequency of those ecosystems to the point that it's favoring highly flammable invasives coming in the post-fire succession. So suffice it to say that there are a lot of reasons why current fire regimes are actually almost the exact opposite of what you would need for a more balanced ecosystem and a more balanced connection with fires on the natural landscape. And then, of course, there is also climate change, which is what I'm going to focus primarily on in this conversation today. I am a weather and climate scientist, and this is what I study. But the other reason, too, is that, as I mentioned, these other two factors, while very important in some contexts, it does depend on the regional setting. So, for example, population expansion in high-risk zones is hugely important where it's actually occurred, but we're also seeing increases in fire severity and activity in very remote regions that have not seen population expansions. Likewise, we are seeing large increases in fire losses and severity in places that are not directly affected by historical forest management and fire exclusion policies. In fact, we're seeing this even in places that aren't forests at all. So those two factors can be quite important, but their importance varies greatly from event to event and across the landscape. But climate change is there pretty much all the time, everywhere, across ecosystems, remote areas, populated areas, you name it. So it's sort of an overarching cause here. And of course, where are we now? Well, this is a map updated as of December, so it's the latest global temperature map since the early 1900s. There's a lot of orange and red on the map. It's a lot warmer than it used to be. The Earth is warming, of course, but the important part for wildfire actually, it often isn't the temperatures themselves. It's some of the second order, the secondary effects that arise from these warming temperatures. Of course, the cause of the warming is the accumulation of heat-trapping greenhouse gases in the Earth's atmosphere, generated almost entirely by human activities. And the Earth has warmed on a multi-decadal average basis, which is sort of how we define that number to be comparable to IPCC targets or reports or something like that. As of 2022, we were around 1.3 degrees centigrade or about 2.5 degrees Fahrenheit of global mean warming. Although the last couple of years have been considerably warmer than that, more like 1.5 degrees centigrade, so more like 3 degrees Fahrenheit, and even a little more in recent months. The other thing that's, I think, apparent from just glancing at the global map is that the rate of warming is not the same everywhere, but that almost every place on land, which of course includes all places at risk of wildfire because there are no wildfires in the oceans, is warming faster than the global average. So when we say that this year, for example, is around 1.5 degrees centigrade warmer than the pre-industrial baseline temperature, that actually means that in any given place on land where people live and where fires occur, like California, the warming is actually considerably greater than that amount. And we remain on a path at present to around double the amount of warming we've seen so far. And the impacts of doubling the warming will likely be a lot greater than a doubling of the impacts because some of these things that we've been starting to see as we get close to 1.5 degrees of warming are processes that can accelerate as the temperatures continue to rise. And so one of these is the changing character of precipitation, which is actually expected to increase on average globally as the Earth warms, not particularly dramatically, but about 2 or 3% per degree centigrade of global mean warming. But the more important part, and I don't want folks to focus on the details of these maps, but mainly just to glance at the left and glance at the right and see that they're different because the left is the projected change in average precipitation per degree of warming, and the map on the right is the projected change in extreme precipitation per degree of warming. And the main thing I want to emphasize here is that the map on the left, the mean precipitation change, there are negative and positive numbers here. There are places where we strongly expect precipitation to decrease in a warming climate, and other places where it will strongly increase. But that the map on the right, it's almost all green. It's almost all positive numbers. That the wettest wets get wet almost everywhere, even in places that might actually see less precipitation on average. And interestingly, California, if you zoom in a little bit, actually falls right at the margin of very little projected change in average precipitation, but a large increase in the most extreme downpours. Now, you might ask what this has to do with wildfire because it might be a little bit counterintuitive. But in fact, this very same mechanism also uh, results in increased rates and increased intensity of evaporation. So in other words, we see that there is a little bit of relative humidity decrease over land, although this isn't really what's primarily driving it. Instead, it's a more fundamental aspect of the thermodynamics of warming air. Essentially, what happens is as the temperatures rise, the propensity of the atmosphere to act as a giant sponge and extract moisture from the landscape rises exponentially. So, with each degree of warming, it's a percentage increase in the atmosphere's ability to do so. So, again, about 7% per degree centigrade, which means about 3 or 4% per degree Fahrenheit. Once we start seeing a few degrees of warming locally over land, which is what we've already seen in Fahrenheit in California, that starts to become a pretty significant number. This essentially is the crux of what my colleagues and I have termed the quote expanding atmospheric sponge effect. And you can really visualize this as the atmosphere acting like a progressively larger kitchen sponge in a warming climate. The net effect of which is that there is an increased ceiling not only on precipitation intensity, which would be analogous to having a larger sponge saturating it with water and then perhaps wringing it out, the wrung out water being the heavier precipitation, but also on the evaporative demand by the atmosphere, the thirstiness of the air itself, probably analogous to a larger kitchen sponge that is not saturated, but still retains the capacity to absorb more water than your smaller one. And so, in this way, in a warming climate, the atmosphere becomes both thirstier when it's not raining, but also capable of much heavier downpours when conditions are right. And so, all of this leads to what my colleagues and I have termed hydroclimate whiplash, which we believe is strongly going to increase in most global land areas as temperatures rise. In fact, we expect that this increase will be strongest in general over land and will probably accelerate somewhere between about 1 and 3 degrees centigrade of global mean warming, which is right around, as you've noticed, where I mentioned we are today. So to zoom in a little bit on California, California's got a bit of a weird climate from the context of continental North America and much of the rest of the world. You may have heard that California has a quote unquote Mediterranean-like climate, and that is because there are so few regions on Earth that have similar climates that most of them are referred to having a climate similar to the Eastern Mediterranean because there's really only one prototypical example of such a climate. Now, there are a few regions on Earth that are similar, Central and Southern California, the Eastern Mediterranean, the Southwest Cape of Southern Africa, small portions of southwestern and southern Australia, as well as coastal Chile. That's about it. That's a comprehensive list of places on Earth that have a climate similar to California, particularly when it comes to hydroclimate. And the reason for this is that California, as well as these other regions, exist at the margin of a stable subtropical climate regime. Sort of think about Baja California and places to the south, and the active mid-latitude regime. Think about Seattle or Portland or something like that. But this boundary is not fixed in time or space. It wiggles around from week to week, even within the winter season, from season to season, winter to summer, for example, and even year to year. Some winters the boundary is farther south than others. That's why we have some winters that are very wet, some winters that are very dry. It's also why we have the seasonal cycle of precipitation that we do in this part of the world, warm, dry summers, and usually cool, wet winters. That's because this boundary shifts northward in summer and then southward to encompass at least parts of California in the winter. It gives California the strong seasonal cycle and also the strong latitudinal north to south gradient in how much rain occurs. It also means that California is very susceptible to year swings in precipitation and therefore drought. So California, of course, has already warmed considerably. This is a map, again, this is a time series. It's updated with the most recent data up through last summer. And summer heat waves have clearly become a lot hotter and longer than 20th century heat waves in this part of the world. In fact, all of California's top three hottest summers on record going back to the late 1800s, have now occurred in the past decade. And the two hottest on record have occurred in the past 4 years. So it has been a particularly hot period in summer across especially the interior of California and at higher elevations over the past 5 to 10 years. Same period during which we've seen such a dramatic escalation in wildfire activity. And yet, when we look at some of these hydroclimate time series over the same period of time, they look a little bit different. We don't see a large decrease in the average annual precipitation, which is what's shown here. A little bit of a decrease in recent years, but in the long run, it's extraordinarily small and pretty minor compared to the level of year-to-year variability. But speaking of variability, we do see an increase in the year-to-year swings from wet to dry and vice versa in the state, particularly if we look during the end of fire season from late summer through early winter. We also see over the same period a strong trend, as you might expect based on recent experience, towards more frequent and more severe droughts. And yet, what I want to point out here is that all of this is occurring absent large changes in annual average precipitation, which interestingly is consistent with climate models which projected that there wouldn't have been much of a trend in average annual precipitation at this point. So what gives? Well, blame the expanding atmospheric sponge. I'll come back to that in a moment, and the increasing ability of the atmosphere to evaporate the water that does fall during our rainy season. So why do we care about this notion of swings between wet and dry and whiplash? Well, an example from Southern California in late 2017, early 2018, with the Thomas Fire, which was at the time the largest contemporary fire in California history and a very destructive one, which was immediately followed by an extreme rain event in Santa Barbara and Ventura counties that caused catastrophic debris flows that killed far more people than the fires themselves. But if you only take a look at the climatological average and the statistics of this 2 month period, you might characterize it as a typically mostly sunny period with some breezy conditions, with below average precipitation overall. So really just want to illustrate using this example that if we only consider changes in average climate, that we're quite often going to miss the point when it really matters most. Another example from Northern California that folks may be slightly more familiar with, and I'll just sort of step through these images because every couple of years I add a new one. I've been having some version of this slide now for the better part of a decade, and we've gone from record drought to extreme wet and almost losing the dam structure to the worst wildfire in state history to another historically severe drought to extreme wetness again, and probably could have added yet another panel for 2024. We're starting to live this for real, and we have certainly recent examples of this unfolding and what the consequences are in different parts of the state. So in California, the projected precipitation on average, as I mentioned, is not necessarily expected to change greatly, but those very same climate models that predict little or uncertain changes in the average annual precipitation predict large increases in both the wettest winters and the driest ones, and thirdly, in the swings between these wet and dry winters, particularly in central and southern California. So this is not, in fact, a contradiction in term. These are not different climate models telling us different things. These are the very same climate models telling us something that is very interesting and a bit counterintuitive, which is that despite the change, a little change in mean precipitation, the increases in the extremes on opposite ends of the spectrum are essentially mathematically canceling each other out. Now, in practice and in policy, they're not going to cancel each other out because what it actually means is we spend more time farther from the mean. We spend more time experiencing extreme drought and more time experiencing severe flood risk, less time in the middle where we don't have too many problems. So what it actually means is that only looking at changes in the average might be quite misleading because it actually doesn't tell us what we need to know about the risks of extreme events like droughts and therefore also wildfire. And I'm going to zoom through this, except to mention that this is even true in a north-south sense in California, where the commonality primarily is that the variability in precipitation during winter, which is indicated by this map on the right in terms of percentage change, is likely to get even more variable from month to month during the rainy season, as well as from year to year. So as I mentioned, why are we worried about increasing drought if precipitation isn't decreasing? Well, just look at the broader Southwest. This is for all the states on the left that comprise the lower Colorado River Basin, which we've heard is experiencing a quote unquote mega drought, which you can actually see in the plot on the bottom, indicating that almost all recent years since the early to mid 90s have been severe drought years, with only very brief exceptions. But notably during this period here too, precipitation essentially hasn't changed, which really tells us that it isn't large decreases in precipitation that's driving this. It's the very large increase in temperature and associated atmospheric demand, meaning that the same amount of rain and snow just doesn't go as far as it used to. And the reason for this is that droughts essentially used to be hot or cold, but well, now they're pretty much all hot droughts, since it really isn't cold anymore in the context of the 20th century climate. So as I mentioned, you can really blame the dry side of the expanding atmospheric sponge for this one. And when it comes to wildfire, I just have one slide on the global picture because I think it's important context. There hasn't necessarily been a very large increase in extreme fire weather everywhere on Earth. On the other hand, there are almost zero places on Earth where there's been even a small decrease in extreme fire weather conditions, and there have been a lot of places where there's been a large increase. The western US, the central US being one of them. This map, by the way, only extends through 2020. If we'd extended it through 2025, you'd see expanded reds in the western US, expanded reds into the Canadian and Siberian Arctic, and also expanded reds in eastern and central Australia. So this is a challenge that is global in scope, that doesn't affect every region the same, but there are essentially zero places on Earth that are seeing a decrease in extreme fire weather conditions in a warming climate. And the reason for this is not that all of these places are seeing less precipitation on average. In fact, some of them are seeing more precipitation on average. Instead, it's that atmospheric sponge effect. It's the thirstiness of the air itself, driving increased rates and intensity of evaporation in almost all fire-prone regions globally, and even some regions that were not particularly fire-prone. Consider the big red blobs, for example, in the Amazon and African rainforests. So we know from science that's been conducted over decades that there is a bit of an exponential relationship between vegetation dryness, here referred to as fuel aridity, since vegetation is fuel in the context of wildfire, and this is driven by fairly well understood properties of combustion, the chemical reaction that is fire. And we actually now, this was originally demonstrated using laboratory studies, and somewhat amazingly, we now see this relationship in empirical data looking at forest fires and the conditions under which they burn in the western US since the 1980s. It's very clear that the relationship between actual forest dryness and fire intensity in those forest environments, or acreage burned as well, is indeed exponential. And the challenge is that as we shift towards a far drier fuel aridity profile much of the time in most of the western US and in other similar places globally, we're sampling more and more from the very dry side of that vegetation dryness distribution. And in the near future, we may see years that are even drier than the very driest years that we've seen over the past decade or so. And one important consequence of this is that it was once thought that future fire increases would be partly mitigated by vegetation feedbacks, by negative or self-mitigating ones. In other words, there might be a big initial pulse in wildfire in a warming climate, but pretty quickly it would literally burn itself out as the fires consumed more fuel faster than the vegetation and the ecosystems were able to regrow. But increasingly, it appears this is probably not the case in most places, because while you may see major changes in the type of vegetation that grows back immediately following a fire, in this whiplash environment, where we still get plenty of precipitation in some years, but ever drier conditions the rest of the time, those wet years still provide ample opportunity for those grasses and brush, especially, but also the trees in many of these settings to grow back rather quickly. In fact, perhaps even faster than before. And what this means is that even several years after a major fire, the landscape, while it might not have regrown a mature forest, of course, in just 4 or 5 years, it might have regrown head-high brush and grass that is plenty liable to burn during the next severe drought and wind event. And this is, I think, reflected in a number of the recent, relatively recent fire locations that I've visited over the past couple of years, including just yesterday, the CZU complex, especially on the coast side, where the redwoods, of course, appear to be doing pretty well. That's the positive news and the success story in Big Basin. But many of the other tree species are not reseeding and resprouting to the same degree. We know that redwoods are historically very fire resilient, and some of the other species in the region are not. But one of the things I found so striking is that following several very wet years in Santa Cruz and San Mateo counties, that the fire footprint has completely filled in. And I started walking on one of these trails and had to turn around because it was completely overgrown with brush and poison oak that was above my head. So it doesn't take very long, and I think part of the reason why this is a bit of a blind spot historically in some of these studies is we didn't really take into account this whiplash effect to the extent that we probably should have. But even not accounting for it, we still have already seen a large increase in the extreme fire weather conditions in this part of the world, a doubling in extreme fire weather conditions in autumn in California since the 1980s. So certainly nothing to sneeze at. That's a doubling is a pretty large increase in anyone's book, I think. Uh, and in California, this is something that is unfortunately quite consistent with climate model projections as to what might have happened up through the present. And this is a trend that appears quite likely to continue on our warming path, as I mentioned, still currently on a path to roughly double the amount of warming, which at the current level of warming has resulted already in a doubling of extreme fire weather conditions a further doubling of the warming would likely result in an even larger increment, more than an additional doubling. So, it's a doubling of a doubling. We're talking about very large increases with warming, and this is one of the reasons why we've got such a problem at the moment. So this is something that I think it was probably Jerry Brown a number of years ago who termed the new abnormal for California wildfire, and I do prefer that term to the new normal because it really conveys the fact that the present, although it is already different from the past, is not a good heuristic for the future because the future will be still warmer and we will see different risk profiles 10, 15, 20 years from now than we see today. So if we want to be proactive and get ahead of what's happening, we really do need to be looking forward, not just trying to catch up with what has happened already. And there's a couple of other aspects of whiplash I think that are important to understand in the wildfire context. One of which is that we have already, of course, a sharply seasonal rainy season in California. It's wet in the winter and dry in the summer, and autumn and spring can kind of go either way. Usually, the later in autumn it is, or the earlier in the spring it is, the wetter it is, and vice versa. But these very same climate models that, again, don't project a large change in annual average precipitation, but do project increasing swings from year to year, also project that our seasonal sharpness, if you will become even sharper, with drier autumns that are already kind of dry and drier springs that are already fairly dry, but potentially a wetter winter. This leads to yet another mechanism for vegetation growth whiplash. Still plenty wet and still a nice growing season in winter and early spring every year, but an even longer drying and curing season to dry out all of that additional grass and brush that has grown during the wet periods that will still come. This has major implications for a variety of practical reasons, but I really do think that wildfire is chief among them. And I'll go into a little bit more about why that's the case now. We have in California, because we have such a strong seasonality of precipitation, we have a vegetation dryness seasonal cycle that is fairly predictable on average. The vegetation dryness peaks in winter to early spring, either during or just following the wettest time of year, as you'd expect. Then those grasses grow and then start to dry out. You get your golden hills starting in June or July, but the vegetation is still wetter in June or July, residual with moisture from the wet rainy season. Then it later becomes in August and into September. And in many years, it remains dry in a lot of California well into October and occasionally even into November in Northern California and sometimes into January in Southern California. And so fire season is a little bit more variable once you get past October 1st, but some years it can extend into December or January, as it did this year in Southern California. Other years, if you get lucky, like 2 years ago, we had that tropical storm in Southern California in August that kind of short-circuited the autumn fire season because it rained 2 or 3 inches in August, and that pretty much put the kibosh on the rest of the year. That was a fortuitous event. But the challenge here is that in years where we do have considerable vegetation dryness leading all the way into October and November or beyond, that is also California's offshore wind season. Santa Ana wind season in Southern California, Diablo wind season in the Bay Area, these warm and dry and sometimes strong to violent offshore blow dryer winds that are often associated with some of our most destructive fires in the wildland urban interface, both in Northern and Southern California, as well as up in the Pacific Northwest, too. So the question here is, well, who wins the race? Does the onset of the rainy season win, or does the onset of the wind season win? Because if the wind season comes first and vegetation is still at or near peak seasonal dryness, then it might be off to the races. And we saw that this year in Southern California all the way into January because the rains were so delayed. And just some personal perspectives from observing and studying fires myself is that this is actually one of the most important predictors of areas that see a catastrophic wildfire despite not having had a very extensive history of major fires in the region in recent years. Because some of these places are places that are fairly wet on average, but every once in a while get very dry during the windy season. And I think that a good chunk of the peninsula I think qualifies in this area. Of course, the CZU complex was a very destructive and hugely disruptive fire that there is a recent history of this. But prior to 2020, think about the relative lack of destructive fires in the Santa Cruz Mountains, in San Mateo, Santa Cruz counties in the last several decades. There have been a few fires that caused some damage, but generally speaking, nowhere near anything on the scale of elsewhere in the state until 2020. And even now, on the eastern slopes of the Santa Cruz Mountains in San Mateo County, Santa Cruz County, and elsewhere, we still don't have that recent history. And that does include places like Los Altos and Los Altos Hills and all of the communities that are on the eastern slopes and along the crest up along Skyline Boulevard. And I'll skip through this part because this has a little more to do with some other regions. But I really wanted to emphasize one more aspect of the seasonality here, which is that uh, prescribed fire we know to be a particularly helpful tool to both, in many settings, reduce the risk of unwanted destructive fires and also, in many cases, improve ecosystems and make them function uh, more like they would have functioned without human intervention. And the challenge here is that we know that there has to be essentially a set of Goldilocks conditions to do under which we do prescribe fire, for example. So essentially, you can imagine if it's soaking wet, you can't constructively burn anything. Imagine trying to start a campfire with soaking wet wood, not going to happen. But it also can't be too hot, dry, and windy, or you have unacceptable risk potentially. So what you want to do are prescribed burns under conditions that are dry enough to get the kind of combustion that you want. Where there's enough wind to ventilate and not smoke people out in the nearby neighborhoods, but not so dry and windy that the fires get out of control and do anything you don't want them to do. So, in other words, you're sort of trying to do an optimization problem of not too wet, not too dry, not too windy, not too hot, not too cold. So, there's a range of conditions. And when we look at how the frequency of being in that favorable range of conditions for prescribed fire changes over time, we find that climate change is probably decreasing pretty significantly the total number of prescribed fire days that are favorable for implementation across most of California, again, including pretty much all of the Bay Area and the Santa Cruz Mountains, as well as much of the rest of the West. But there are two caveats here. One is that if you look at the winter map, it looks very different than the annual map and the summer map. In fact, there are some regions, including some in the Bay Area in Northern California, where we actually might see an increased number of days favorable for prescribed fire in winter, which is historically not the most common season to do it, but it might actually offer an interesting opportunity to do safe and effective prescribed burning if we can pivot to different times of year. And I know that's already started to happen in some places in winter. One challenge is that on federal lands, federal fire crews are often seasonal and are not present in winter, but at state lands, it's a bit of a different story. The other point is that we actually don't use very many of the prescribed fire favorable days that are already available to us in the present climate. So, in other words, even if we lost half of them, if we got better at using the days that are available, we could actually increase the number of prescribed fire days that we actually take advantage of, even if they become fewer and farther between. So, to talk a little bit about Los Angeles, one of the reasons why the situation was so bad in January, yes, it was extremely dry in the months and the weeks and the days leading up to the fires themselves, record dry, in fact. But the other challenge here is that we also had what I'm calling wet to dry precipitation whiplash, hydroclimate whiplash, over the 2 years prior to the fire. So 2023 and 24 were some of the wettest years on record in Southern California. In fact, the 18-month period at the UCLA climate station ending in June 2024 was literally the wettest 18-month period that had been recorded there. That led to abundant accumulation of what are known as herbaceous fuels, essentially grass and brush. Because as you imagine, in a place that's often quite dry, the plants are adapted to take advantage of the wet periods that do occur and grow like gangbusters. Makes for great wildfire blooms, but the challenge is when a record hot and dry period follows, which did this time around, that desiccates that enormously abundant vegetation loading. There is literally more biomass, more fuel for the potential fires to come, and boy, did they come, given this context of record dryness and then an extreme wind event that immediately followed. That's what set the stage for what transpired there. And what we actually found, just in taking a quick look at this, is that we do indeed see an increase both in the average dryness in December, Southern California, over time, but also an increase in the variability of that moisture in late season. In other words, the likelihood of swinging from wet to dry or dry to wet quickly, which is exactly what helped set the stage for January 2025 events. We've actually seen about a 25% increase in the magnitude of those swings in Southern California at the peak of fire season. And also, we've seen that the general or that the annual maximum uh, fire weather conditions during, I guess we could call it Santa Ana wind season, which runs from peaks in about November through January down in the LA area, has itself increased by about 36%. So the most extreme fire weather conditions during winter, which is when these Santa Ana winds blow in Southern California primarily, is about 36% more intense than it was in the early 80s. Again, that is not a small change. And I just wanted to emphasize the just what sort of the reality on the ground was during these events in California and Southern California this January. This is the Ember Storm on the Eden Fire. So this footage is from a Ring doorbell camera. And what it illustrates are hurricane force winds blowing literally billions of embers into a neighborhood that eventually completely burned down in Altadena. And I think I'll replay this once just because I think it's worth seeing. Essentially, this is what you're up against. When you hear about home hardening, when you hear about ember resistant vents, when you hear about keeping vegetation clear in that 5 foot zone zero, this is exactly the kind of scenario where all of that comes into play. Even if you're not directly in the wildland, even if there's not a lot of contiguous vegetation near your house, there wasn't here either. And look at that. These embers are just landing on people's lawns, landing on trees. They're igniting the palm trees. They're igniting the lampposts. They're igniting people's fences and decks, and everything in between. So in this kind of scenario, where it's literally the driest it's ever been, where there's more fuel than we've had in decades, and then we get an extreme wind event. That's the kind of conditions where you really do sort of realize your worst case scenario potentials, and it's where a lot of these mitigations that we talk about end up becoming incredibly important, even in places where on an ordinary day you might think they're a kind of overkill. So, just a few lessons. There was extreme structure loss, of course, on these fires. We know that over 18,000 structures were destroyed or damaged. The loss of life exceeded 2 dozen, and that's just direct toll. The epidemiological estimates for the people who were made ill or will eventually die due to smoke inhalation and cardiovascular disease is likely in the hundreds or even greater, with record-breaking economic losses on the order of, at a very minimum, tens of billions of dollars for direct insured losses, and there are some estimates that the indirect economic cost will probably exceed $100 billion, making this the costliest wildfire disaster ever in human history. Uh, th- these fires were devastating in a region and even in specific neighborhoods. So again, in Pacific Palisades and the foothills, right below the mountains near Pasadena and Altadena, that were known to be at very high risk of a wildland urban interface event during a high wind condition. So LA, of course, is no stranger to fire. It's part of the it's famous and if not infamous for it. This no real mystery. You live there long enough and you see fires in the distance, but they've long been for most folks in the distance, in the hills, maybe at the urban fringe, not so much directly into the heart of the neighborhoods themselves. Uh, but what caused that? Ultimately, it was still a confluence of known risk factors. These were not mysteries. There was an extreme weather event, both in the short term and medium term. This very strong winds, but also record-breaking dryness, and then the antecedent wetness and abundant vegetation growth immediately preceding it. There is climate change. We're seeing increased overlap between dry vegetation season and strong wind season. We're seeing longer fire seasons and greater whiplash between them. The topography of the region is just inherently favorable to generate winds that blow strongly from the hills down into the neighborhoods that people live in. And if there's a fire, that's just a bad combination. We also know that there was dense urban and suburban vegetation in all of these places. It was not really a place that was designed or planted to be fire resilient. nor were the structures in many cases designed to resist a fast-moving wind-driven blaze, despite the fact that we had long known that these were areas very much at risk of this, at least occasionally or rarely. I think another important lesson is the recognition that under sufficiently extreme weather and climate conditions, there are ultimately pretty severe limits on what you can accomplish, even with very advanced modern firefighting techniques like we have in place during these events. If the wind is extreme enough, for example, you can't fly aerial firefighting aircraft. You can't get the helicopters up. You can't get the planes up. You can't even actually get drones up to monitor the fire. You're stuck with what you can do from the ground, and that too is limited by the winds. Also, and there's been a lot of conspiracy theories and finger pointing and blame about this, but ultimately, the reality is that urban water supplies just aren't designed to fight thousands of simultaneous structure fires on the same municipal water supply. You just can't do it. It's just a fundamental problem of fluid flow, and you would need a completely different water distribution system than generally exists in most populated areas to accommodate that. One place that might actually have something like that, by the way, is the city of San Francisco. Not because the city of San Francisco is per se at a high risk of wildland fire, but this was something that was developed by the fire department, the city fire department, to combat an urban blaze following a major seismic event. So if the primary system is compromised or overutilized, there is a secondary backup system in San Francisco that can draw upon salt water from San Francisco Bay. And that is a very smart intervention for a city like San Francisco that has a history of burning to the ground or following an earthquake. But we don't have those kinds of systems almost anywhere else. And so there's an expectation that, excuse me, that you call the fire department, the engines come, they plug into the hose systems, and they can supply a functionally infinite amount of water. But that's in fact not actually how these systems are built. And so we reached the limit and went well beyond what was possible in these kinds of situations, unfortunately, during both of these fires. And the other lesson that I think is obvious just from watching that short video clip that I just showed is that small spot fires, just a few inches initially in diameter, just a smoldering ember or a flaming palm frond or something, can become uncontrollable within literally 5 or 10 seconds under these conditions. And so these are sorts of conditions where even if you had a fire crew around the block, by the time they got to your house, this spot fire might have already become uncontrollable amid these winds and extreme dryness. So all of this, I think, emphasizes the real critical importance of vegetation management, specifically in populated areas, in people's yards, along roadsides, in city, county, regional parks, for example. And I think that's why it's encouraging to see these kinds of projects like the one that got me stuck in traffic on Page Mill earlier this week, because that is probably one of the easiest and highest yield things to start with. It certainly isn't going to stop a major wind-driven fire in its tracks, but it's going to give you more margin to get people out of harm's way, more margin to get fire crews into where they need to be, and make it a little bit easier, at least in some cases, to defend these roadways and keep the fire from spotting over it in some cases. We also had some near misses, another reason why it's important to take evacuation routes seriously. We almost had a major burnover event in Pacific Palisades with that huge traffic jam. You might have seen the footage of the LA County Fire bulldozer pushing all of those vehicles out of the traffic jam. Once people had exited the vehicles because they needed to clear the road, there was gridlock and people just had to abandon their cars and run. Fortunately, in that traffic jam, everybody, as far as I know, ended up making it out. But had the situation been a little bit different, or this had happened in a slightly different part of the fire, it could have had a very different outcome. And in other places around the world, this was true in the Lahaina fire on Maui and multiple recent fires in the southern Mediterranean and Chile. We have seen lots of people who become casualties stuck in their cars in traffic jams trying to evacuate. And so that is one reason why it is incredibly important to maintain those routes of ingress and egress, and also to maintain them and to be aware of where you need to go and when. And so that's also pointing to the importance of emergency communication, telling people what they need to do in a very timely fashion. I think in what we saw in LA is that We're better off than we were in 2010, but there are still major gaps. People still didn't know where the fire was, where it was headed, and what they needed to do. Watch Duty, the phone app, is probably the most impressive piece of technology to come out of this. I don't like app solutions for most things. I'm actually not a fan in general, but I actually think this is an exception. If you haven't downloaded it, if you don't use it, I would strongly encourage that you do. It's not perfect, but it is, I think, probably better than almost any other alternative in this moment. And so I think the crew at Watch Studio, which is rapidly expanding, by the way, are doing good work and has probably already saved some people's lives, will probably save more lives in the future. And then a couple of closing slides. I think this is especially important in the setting of a place like the eastern slopes of the Santa Cruz Mountains, because there just haven't been many fires of significance east of Skyline Boulevard in many years. But that doesn't mean the risk, at least the conditional risk, is low. It just means that the difference between ordinary and what I'll call extraordinary risks in a place like this are quite different. The ordinary risks on a typical day are not very high. Today, for example, there is virtually zero risk of a destructive or deadly wildfire in the region. But that's partly because, well, it's early May, the vegetation is still damp. It's not windy, it's a little bit of a sea breeze, but nothing too bad, and the air dryness, the air temperature, are quite mild. So there really isn't anything to worry about at all on a day like today. But think about a day like they saw in LA. Think about a record-breaking heat wave following a severe drought or an extreme wind event, which on the peninsula would probably be something that happens in September or October or maybe November. Imagine it's a historically severe drought. The situation then would be very, very different, and that's why it's so important to prepare in moments where the risk is low, because that's when it's easiest to do the needed work safely. But I think that this speaks to a broader challenge, is that the places at most risk of catastrophic fire under extraordinary conditions are not the same as the places most at risk under ordinary conditions necessarily. There's some overlap. LA County has a lot of quote unquote ordinary fires, as well as the unfortunately extraordinary fires we saw this year. But there are other places. Yesterday, for example, I was in Half Moon Bay, and you realize when you see the eucalyptus groves on the east side of town that this is a place that's usually cool and foggy and damp and at virtually zero risk of a dangerous wildland fire. But you can imagine during a severe drought, during a major wind event in October, were there to be a fire ignition in those eucalyptus groves, that it could very much and very rapidly threaten much of a place like Half Moon Bay. And this is reflected in the new CAL FIRE hazard severity maps that came out this year. Eastern part of Half Moon Bay is, in fact, in the high severity zone, as I think it should be. And these are, interestingly, things that folks have pointed out to me as being they perceive to be quite ridiculous. How could Half Moon Bay possibly have higher fire risk than some communities in the Sierra foothills, for example? And it's not that the likelihood of a fire there is higher, it's instead that the plausible worst case scenario is, in fact, potentially worse there because of the vegetation setting and the combination of conditions that could occur under unusual conditions. So again, in California and beyond, where does these underappreciated hotspots risk? It's often in places that are usually quite moist, but with very dense vegetation, but that occasionally or even rarely experience very dry conditions with strong winds. So the classic low probability but high consequence type of scenario. So just to sum it all up, it's really important to think about whiplash and the seasonality of things and consider the nonlinearity. We know that wildfire trends are multifactorial and they're complex. Climate change is definitely a piece of this, but it's far from the only thing that matters. And that also includes population expansion in high-risk zones and various historical policies that upped the ante on the risk. And that while this kind of risk is highly variable across events and in contexts, the climate change component is almost always present, and sometimes it's quite large. And that from a wildfire perspective, a lot of these shifts can sometimes have a net effect that's larger than the sum of its parts. So I'll skip through this. This is more for an academic audience, but I just wanted to close with this final slide, which is to point out that wildfire itself is not the problem. It's not inherently bad. It's a natural process that in many settings we could actually use more of. if we want to see less risk and healthier ecosystems. But it's the intersection between wildfire and populated places that has become increasingly problematic and in some cases genuinely catastrophic. So, and we also haven't seen the worst of what's possible. I've again created this slide, a version of it, and updated it every couple of years with a new event. So I think the burning question really, literally in this case, is not so much can we decouple fire from catastrophe, because we know from some success stories that it's possible. The question is, will we do it comprehensively enough and quickly enough to get ahead of the climate change curve and get ahead of all these other things that are shifting in a direction of increasing risk? Can we outrace the hazard? And I think the answer is that we can. So really, instead, the question is, are we going to do it fast enough? Will we do it? I hope we do. And so with that, I think I'll close, and hopefully there's time for a little bit of discussion. Thank you.
Thank you, Dr. Swain. That was amazing information that you gave. Denise Fluin, Community Education Risk Reduction Manager. I'm going to ask the audience now if they have any questions for Dr. Swain, and then we'll follow that up with if there's any online questions, if that's okay. Anything in the audience at this point? I know it's a lot of information. Hold on just a second. I'll give you a microphone here.
Yeah, thank you, Daniel, for this. I have a question that's not directly tied to your presentation, but I read your musings, and if you wouldn't mind, we're seeing a lot of job elimination in NOAA and some of the climate science agencies that follow and help us track and predict risk, and just any thoughts that you might want to share relative to that.
Yeah, I mean, if you do follow me online on Blue Sky or YouTube or something, you've sort of seen that I've been reflecting with rapidly increasing alarm at the seemingly almost a complete dismantling of some of these federal emergency response and predictive entities, including even things as fundamental and basic as like the National Weather Service, which apparently, as of this week, is no longer a 24/7 operation in some parts of the country, which actually even I was shocked by. I mean, that's a huge shift even from last week. These are expanding, and we have not seen the end of it. In fact, we haven't even seen the full impacts of a lot of the cuts that have occurred, and there are credibly rumored to be even larger ones to come. And we are on the cusp of just fully dismantling a lot of these services. And obviously, there's a lot of reasons why this matters. But one of them is with respect to something like wildfire. So imagine, for example, what the LA fires would have looked like if there hadn't been a warning of extremely critical fire risk conditions in LA County days before they occurred, if there'd been no pre-positioning of firefighting resources, if the city of LA had not closed some of these open park areas to visitors to prevent ignitions, or had not prevented street parking that would have prevented ingress and egress for fire engines and for people needing to evacuate. All of these things were things that happened in advance of the fires, and we did see catastrophic fires, unfortunately, nonetheless. But imagine if there had been even just one additional fire catastrophe at the same time. How much worse all three of them then would have become due to lack of resources and even fewer places to go in between. Just that one event, even just averting one major fire in that outbreak, which I'm quite confident probably occurred due to these preemptive actions that occurred as a result of these National Weather Service predictions, for example, uh, almost justifies the entire Weather Service budget for a good portion of the U.S. for the entire year. Just the cost savings associated with one fewer disaster or one less severe disaster. This also matters because there are, from the Weather Service on large wildland fires, there are deployed what are called incident meteorologists, or IMETs, that come from local offices, field offices from the Weather Service all around the country. And these are expert meteorologists that are essentially brought to the fire lines, to the fire camps, where the fire crews have sort of the organizational and logistical base to provide in-house services, weather predictions, forecasts for burn operations, for evacuations, for just about anything you could imagine. Um, we may not have those folks available beginning this year on large fires because they're needed elsewhere because we don't have enough people to even staff basic operations like issuing tornado warnings and flash flood warnings or things like that. all around the country. And if there is a major hurricane coinciding with major wildfire events later this year, that's going to be a real problem because we'll be understaffed at NOAA. We have a lot of red-carded federal employees at the Forest Service and elsewhere. These are folks who they don't have a firefighter in their job description, but they are nonetheless trained in wildland firefighting and are often on the lines in these fires doing wildland firefighting work. A lot of them were fired or let go in recent months. So we have, although there are claims that the federal forestry technicians and firefighting units haven't been decimated, the reality is that a lot of the folks who actually end up on these fires are no longer in those roles this year. FEMA too is being picked apart piece by piece. So I know this is a bit of a long response, but I just wanted to emphasize that this is very concerning and has major implications, potentially even for the current fire season, in California and beyond. California is lucky that CAL FIRE exists. There is an in-house state-operated wildland firefighting agency, but California also has a lot of federal land, and California still depends on federal assistance during major disasters. And so, the Weather Service is also a federal operation. So the short answer is I'm very concerned about all of this, and I think it has immediate and direct relevance for wildland fire in California.
Please.
Thank you so much for that presentation. I'm an avid follower on Blue Sky. I really enjoy seeing you in person. What are your thoughts about the upcoming wildfire season here in California?
It's a good question. It's the million dollar, I guess maybe the multi-billion dollar question. It's one that insurance companies are asking all the time now. I think it'll be an interesting one, and that it'll probably be pretty different depending on where you are in California. Um, Potentially even a delayed start up in parts of Northern California that were quite wet this winter, especially north of the Bay Area. Maybe an average start in the Bay Area, nothing too extraordinary in terms of when. But we might see this whiplash dynamic play out because we've had a particularly wet winter now, several years in a row in Northern California too, not just Southern California. And this whiplash metric, where the vegetation growth preceding the dryness, that plays out most dramatically in places that are predominantly characterized by grass and brush. And so, in Southern California, that's a lot of what's in the environment. But there are large regions in Northern California where that's true too. It's often on the fringes of forests and or in the foothills ringing the Central Valley, up in Lake County, a lot of that is heavy brush. So what I would expect is that we have a lot of, I guess you could say, a lot of herbaceous fuel loading from the last few years in a lot of places. So a lot of extra grass and brush growth. It isn't particularly dry right now, but we also have an expectation that this summer, especially the second half of summer, will be particularly hot into the fall. And that's where we might actually see some places where there's a slow or below average start to fire season, but a well above average finish. In Southern California, this is probably going to start earlier because we didn't really get much rain this winter down there. So an early and more severe start to California, Southern California. But in Northern California, it's going to be ecosystem dependent. I wouldn't really expect this to be a big fire year in the High Sierra or in the really dense coastal redwood forest. We don't have a drought in those places right now, and these places are not unusually dry. But in the grasslands and in the brushier parts of Northern California, we actually could have a very active fire season, but likely not really revealing itself into the latter half of the season. Southern California, a bit of a different story. High Sierra, probably maybe even a below average season. So I think one of the things is we're getting more sophisticated about making these kind of nuanced predictions based on the type of ecosystems that we're talking about and sort of the quadrant of the state, because it really is a big state with a lot of geographic and ecological diversity, and also a state where the weather can be doing very different things. The northeastern California, the plateau region, for example, this last winter was essentially the wettest winter on record. In some parts in Southern California, it was the top 10 driest winters on record. So just very different worlds right now.
Right, thank you very much. I don't think we have any online questions. Any else from the audience? Otherwise, thank you again. Really great information.